Greetings, physicists. This video will be about how to solve these static equilibrium problems. So, start with a dude who's going to lift a bucket of rocks with a lever, essentially, a big heavy, well, it says a big lightweight beam, so we are apparently ignoring the mass of the beam. Not because it has no mass, but I'm assuming because it's much less than 910 kilograms, which is what he's lifting. So, let's draw this. This is one could be hard to visualize, but essentially you've got a beam attached to a pivot, and then they hang a bucket of rocks from it. So real heavy rocks in the bucket, and the dude comes along and lifts it because he's super strong, and the bucket is like hanging there. Okay, and we know the mass of the bucket, so the mass of the bucket will be 910 kilos. We're not going to assume that the beam has any mass itself. From the pivot to the bucket is 0.85 meters. From the pivot to the dude, 3.6 meters. Okay. And he holds it steady, and that's the key that this is in static equilibrium. So how much force does he use, and how much from the pivot? Well, we'll consider the beam to be the system here. If we look at the beam, it's got an mg down from the rocks, it's got a force up from the man, and it's got a force up from the pivot. And we're not going to consider its own mass because it said it was lightweight, and that's our hint. So there's two things we've got to do. We're going to have to do a free body diagram. Free body diagram is just the forces, and we have mg down. We have the dude's force, and we have the hinge where the pivot is supporting the other side. And those have to balance out, right? Because the thing is not moving up or down. It's in static equilibrium. So sigma F has to equal 0, which is only true here if the force from the man plus the force from the pivot equals mg. And we're looking for both of those. We want the man's force and the pivot point's force. And since this equation is two variables, we can't really use it. But we can also do a sigma torque equation. Sigma torque has to be equal to 0 because if he's holding it steady, it's not rotating about the pivot point. Now, we said in the lecture video that you don't have to choose the pivot point to be the pivot point. You can choose any point there to be the pivot, and the torque will still be 0 about any point. I will use the pivot in this video, and the reason I'm going to use the pivot in this video is it just, with the numbers they give you, it makes it really easy. They have a radius to the bucket, and they have a radius to the guy. So those numbers are already given. So our torque's about the pivot point. Well, the force up on the pivot itself does not create a torque because it's acting on the pivot. The radius is 0, essentially. And so by choosing the pivot point to be here, I eliminate the torque from this force, which will make my calculation easier. So when I go down here to my sigma torque, the mg down produces a torque in this direction, and his force up produces a torque in the opposite direction, so they have to be equal to each other. So we'll say the torque from the man has to equal the torque from gravity. Oh, come on now. Torque from gravity. And we know that's going to be that his force will be, or his torque will be his radius, the man's radius from the pivot cross his force. And we know the torque from gravity is going to be the radius where the bucket is. So I'll just put the radius of where gravity acts times his force, gravity's force, which is just mg. And we're looking for this one, so I'm going to go ahead and solve this equation for F, and I will get the man's force should be equal to the radius at which gravity acts times mg divided by the radius at which he acts. And we have all of those things. So we can plug them in. The radius at which gravity acts, it was the bucket. And gravity here is only acting on the mass that we were given, which is the bucket. So 0.85 meters. The mass of the bucket is 910 kilos. And of course gravity is 9.8, like so. And then the dude's radius, he acted at 3.6 meters. So we should be able to plug that in the old calculator areno. So 0.85 times 910 times 9.8 divided by 3.6, and my calculator is giving me a very large force, because this is a strong dude, of 1982, also my favorite year, newtons. And it's a 2 sig fig problem, so we're really rounding this to about 2,000 newtons of force that the man exhibits. All right, that gives us one of the two we're looking for. The other thing we were looking for up here was the force of the pivot. Well, I can go ahead and redo a torque equation and set the man's force equal to, like, make the pivot somewhere else. Or I can just solve this equation here, which is what I'm going to do. So let's give myself some room, because now I know the force of the man. So force of man plus force of pivot equal to mg. I'm solving for this guy, so let's subtract the dude's force out and get force pivot equal to force man negative force man plus mg equal to negative 2,000 newtons plus the mass of the rocks was 910 kilos. And gravity is 9.8. So calculator says 910 times 9.8 minus 2k, and I'm getting, of course, 69,000 newtons. Well, that's good, right? Essentially, if he started at 2,000 and got up to 6,900, he almost, that's like 3.5 times his force, more or less. Yeah. So the lever, a wonderful invention. And 3.5 times the force should make sense, right? Because the mass of the rocks was acting at a 0.85 meters, and his force was acting at a 3.6 meters. So that is about 3.5 times larger of a radius that he's using. In fact, it's a little more than that. Yeah, because 6,900 is a little more than 3.5 times 2,000. Good stuff. All right. So let's continue on and try this problem. So if you have a garage with a workshop in it, you might have some of these. These are sawhorses. They're just little things that you can set stuff on. And what we have set on them, apparently, is this beam. But we haven't set it evenly. The end of one beam lines up with that sawhorse, but this piece is 1 meter away from the edge, and we know how heavy the beam is. What are the magnitudes of the normal forces acting on the boards? Interesting. Well, let's draw some forces here. We have a normal force up here. We could say that's force 1. We have a normal force up here. We could say that's force 2. Counteracting them is gravity. We've got to think where gravity acts. The board, if it's a uniform board, is 3 meters wide. So halfway between that, maybe about here, is where mg is going to go down. So right at 1.5, or half a meter away from that. So, like any static equilibrium problem, if this board is resting, then it is not accelerating. And so I can do a free body diagram, because I can do a sigma f equals to 0 if I have an F1 up, and then an 2 up, and then downward is the weight of the board, which they told me is 100 newtons. And all that should add up to be equal. So I should say F1 plus F2 has to equal 100 newtons. But the board is not only not accelerating in a linear fashion, but the sigma torque is 0. So I'm going to pick a pivot point here. And it doesn't matter where, but I'm going to pick mine to be right here. Because again, whatever pivot point you pick will work. If I pick this pivot point, here's what I need to know. Force 1 does not cause a torque about that point. So I don't have to worry about including force 1 in my sigma torque equation around this pivot point. Force 2 is this far away. Well, how far is that? That's 3 minus 1, or 2 meters. So I could say R cross F, or the torque around force 2 is, well, let's just do this. Let's say torque from force 2, which is going this way, and then the torque from gravity goes the other way. So this would be torque 2, and this would be torque of gravity. So torque 2 has to equal the torque of gravity in order for the torque around that pivot to cancel itself out. So torque 2 is R cross F. The radius would be let's solve this beforehand. So this would be radius 2 cross F, so times force 2, which would be equal to the radius of G times mg. All right, so let's define those. The radius of G is just 1.5 meters, because the end of the board is halfway from the center. And then radius 2, which is here, would be 3 minus 1. And I'm solving for force 2 anyhow, so it's going to look like this. Force 2 will be equal to radius of G times mg over radius 2, which we have numbers for. The gravity acts halfway, which is 1.5 meters. The mass of the board times gravity. So they don't give us the mass, they don't give us the gravity, they just give us mg total. So that's 100 newtons together. Keep that in mind. Over R2, and R2 is 2.0 meters. Sweet. So, 100 over 2 is 50. 1.5 of 50 is 75. Meters cancel. So 75 newtons. So force 2 is 75 newtons. And if force 2 is 75 newtons, then force 1 has to be 25 newtons, because that has to add up to 100. So that's not too bad. And if we're looking at this picture, force 2 has to be bigger than, so this is force 2 has to be bigger than force 1. Why? Because it's closer. In order for it to support a weight that's right here, it's going to have to push harder, because it will produce less torque per unit radius, because it has a smaller radius. So the one in a bigger radius doesn't have to work as hard to produce the same amount of torque. All right. Good times. Here we go. Let's do another. All right, we got a lady lying on a reaction board. I had to look this one up. I had never heard of a reaction board. A reaction board looks like this. Pretend that I drew it straight. It's got a pivot over here somewhere. And then on this side, there's like a scale. You know, where it like reads off, tick, tick, tick. Like the supermarket scale, essentially. Holding up that end. And then she lies on it with her feet over the support. So here's her feet. There's the lady. Okay. And she has a weight of 600 newtons, so mg for the lady equals 600 newtons. The board is 2.5 meters long. Okay. And the board itself is 60 newtons, so the mg of the lady, oh gosh. So let's just say this is the weight of the lady, and then we'll call the weight of the board is 60 newtons. That's conveniently 10 times less than her, I suppose. And we have a scale over here, so the scale up, the force of the scale is 250 newtons. We want to know the distance d from her feet to her center of gravity. So what distance? Her center of gravity is probably around her hips somewhere. What is that? What is that delta x? I say delta x, but of course we're talking about a torque problem, so what we're really thinking is what is that distance, r? So we'll call that a radius. And we're looking for that. Well, this is a torque, torque problem. This is a static equilibrium problem because she's not moving. So if we draw forces on this, we have the spring force up here, we have the force of the board down here, and we have the force of the lady over here. And those three things have to be in equilibrium because the torque on this has to be 0. Now technically there's also a force up here from the pivot. If I can draw. So there's 4 forces. Now if we make this the pivot, though, when we do our torque problem, the pivot force itself is not going to matter. It's not going to cause a torque. So we can do that and eliminate it. And I think that's best because we are given values for each of these others, which should be fine. So our torque equation then, these two forces here cause clockwise torques, and this force here of the scale causes a counterclockwise torque. So the force of the scale cross the radius of the scale should be equal to the r cross f of the lady plus the r cross f of the board. Okay, so we know the radius at which the scale acts from the pivot. The board, if it's a uniform board, should be half of that. So if we're plugging things in, and of course, what are we solving for? Before I start plugging things in, let's figure that out. We're solving for a radius of the lady. So this is our unknown. So let's solve for that. Give ourselves some room. So the radius at which the lady's force acts should be equal to r cross f for the spring minus r cross f for the board divided by the lady's force. Yeah? And then we know the board's radius. We know all three forces, and we would say, we know the spring's radius. The board's radius, the weight of the board acts halfway along the board. So let's plug some things in. The spring was located 2.5 meters away from the pivot point, and the force applied at that distance was 250 newtons, minus the radius of the board. The force of the board acted half of that, so 1.25 meters, and the weight of the board was 60 newtons, divided by the lady's force was 600. She has a weight of 600 newtons. And if we divide all that, we should get where her center of gravity is. Okay. Well, let's do that in the old calculator. 2.5 asterisk 250 subtract 1.25 asterisk 60, enter, divide 600. This is going to come out nice. All right. And we're getting 0.916666, but essentially this is a 2 sig fig problem. The 60 could be 2. The 1.25 I got by dividing 2.5 by 2, so this is technically like 1.3, but that's fine. So 0.92, not newtons, excuse me, newtons cancels. should be meters. So a little less than a meter from her feet to her center of gravity, which is essentially probably right where I drew it, right above her hips. Okay. Good question. All right, last one. Oh, I love these. A 3-meter long ladder leaning against a wall at an angle 60 with respect to the floor. Let's draw this. We have a wall and a floor and a ladder leaning between them. So there's the ladder. And the angle it makes with the floor, is what it said, was 60 degrees. And the ladder itself is 3 meters long. What is the minimum value of the coefficient of static friction with the ground that will prevent the ladder from slipping? And assume it does not slide between the wall, or that friction doesn't occur between the wall. All right, this is a cool problem. Let's start by identifying some forces on the ladder. There is obviously halfway up the ladder, halfway along the ladder. If it's a uniform ladder, there's an mg. So mg goes down at that point. Where it touches the wall, there's a normal force pointing straight off of the wall. Because normal forces are perpendicular to the surface, and where it touches the ground, there is a normal force. So we may need to not use n because that will get confusing. So let's call this just force wall and force ground. So force wall, force ground. So notice there has to be friction or this thing will slide, because if we do a free body diagram right now, the ground force is pointing up, the mg is pointing down, the wall force is pointing to the right. And that's the only 3 forces. So this would be accelerating to the right. So there has to be some friction. And if friction occurred here, it would resist that motion. It would go backwards. I didn't mean to draw that at an angle. Force of friction, or lowercase f sometimes. So this frictional force would have to be that way in order for this to work. So if this is truly in static equilibrium, you can divide this up vertically and horizontally. You could say that the vertical direction, the force of that's ground, that's not the force of gravity. The force that the ground pushes up with should be equal to mg. I might relabel this force the normal force, because that's even though they're both normal, the wall force and the ground force is the one that's going to cause the friction. It's the normal force responsible for the friction force. So that might be a little better for us. So the normal force that's pushing up on the bottom there will be equal to mg, and the wall force should be equal to the force of friction. And if we have the friction formula, the force of friction is equal to mu times the normal. And I believe mu static, because this is not moving, that's what we're looking for. What is the coefficient of friction? So if I rearrange this, I'm going to divide by n. I'm going to get mu static, which is what I'm looking for, equal to the force of friction divided by the normal. But I can further substitute in that the force of friction is the force that the wall applies, and that the normal is mg. So I have that. The force of the wall divided by the mass of the ladder times gravity. Is that correct? I think that is, yes. Yes, that has to be correct. Okay. So I know m and I know g. The force that the wall applies is not something that is given to me. And so what I really am going to have to do is find a way to substitute in for the force of the wall. Well, I've exhausted all of my free body diagram, but I also have another thing, because this is in static equilibrium, I can do a torque equation. So the sigma torque has to equal 0. Well, let's go up here and see which makes the most sense. Well, look let's pick a pivot point. I'm going to pick this pivot point. And the reason I'm picking that pivot point is there are two forces being applied at that point. The gravitational force, not the gravitational force, the normal force from the ground, and the frictional force. So if I place the pivot here, both of those will apply zero torque. And it will make my calculation easier because the only forces applying torque are this force here, the mg, and this force here of the wall. So I'm going to put those in and say that for my sigma torque, that means that the torque from mg has to equal the torque from the wall. And that would be the radius times the force of gravity has to equal the radius from where the wall attaches times the force of the wall. And that's what I was trying to substitute for. So let's get that guy on his own. That wall force will be equal to the radius at which gravity acts times the force of gravity, which in this case really just is mg, divided by the radius at which, the wall acts. There's also a problem here because this is a cross product. And so let's redraw this just so you can see what I'm talking about. Notice that, and this is also a cross product, so this is R cross mg. These forces are not acting 90 degrees to the lever arm. So we're going to have to resolve those forces. Oh boy. So, or those radii, either way, and I'll show you how that works. So, let's come this way. We'll do a redraw here. Draw it big so I can handle it. I know that's a 60-degree angle. I know that this one is straight down. What I really want is if I'm going to split that force. I'm going to split that force into components because there's a component of it, this component, that is in line with the pivot that will not cause a torque, and then the other component will. So if this were here, if I'm going to say this line is parallel to this line, and this line here would have an angle of 30 degrees there. And then I'm going to do this line here, which means that this is also 30 degrees there, yeah? Yeah. That's a 30-degree angle. Yeah, because of similar triangles. So that's 30, and so we're going to say, geez, that's 30, so that has to be 60 right there. All right. Sorry, this is not fun geometry for me. Maybe this comes more naturally to other people. But we had mg was the hypotenuse, and then this is going to be the adjacent of 60. So we should have mg cosine 60. Ugh. Not fun. So if I put that up here, mg cosine 60. All right. And then the other force, which was the wall force, was this direction. Now, this may be a little easier, because if that angle is 60, then this angle is also 60. So if I split this force into its components, right, the hypotenuse is the wall force, and then I have this component and this component, but this is the one that doesn't cause the torque, and so this is a sine. This is an adjacent, or this is an opposite. So this would be wall force sine 60, which means up here that would be wall force times sine 60, or I'm dividing by it. So this would be, whoops, sine 60. Now, cosine 60 over sine 60 is cotangent of 60. But I think you can flip them. I think you can just do sine 30 over cosine 30, so this could be tan 30. So, if I bring all of this down here, RMG times MG over RW times tan 30. Yeah. RMG times M times G tan 30 over R of wall. Okay, and we now can probably solve this, assuming, again, this is the pivot point, and the ladder was 3 meters. The mg acts halfway along that, exactly at 1.5 meters from the pivot. The wall acts at exactly 3 meters from the pivot, and we have the mass and we have the gravity. In fact, I think we have just the weight, right? Let's go back up and get those numbers. Oh boy, come on. A 3 meter ladder. Oh, wait, maybe it doesn't matter? Hang on. So, well, let's go back to a 3 meter ladder. All right. So essentially, the radius at which, so this is going to be 1.5 times the force of gravity times the tangent of 30 over 3. So this is going to be 1.5 over 3. We'll go to just a half of the tangent of 30. So tan 30 is that, divide by 2, 0.288, about 0.29. I'll carry through this. So this is going to be equal to 0.2887 times mg or the FMG. Okay. We're not done. Gotta plug this all back in. To this. Yeah. And the mg is going to cancel. Good. Okay. So 0.2887 times mg divided by mg. Well, glory be, this is the coefficient of friction. And since this is like a 2 sig fig problem, again, this is going to be equal to about 0.29. No units on a coefficient of friction. This is mu static. So it doesn't have to be that high. I mean, this is a fairly average coefficient of static friction to keep that ladder from going anywhere. If this was carpet, it'd be very easy. Okay, that was a very tricky, long, and involved problem, and I hope I didn't make it more confusing. But hopefully this helps you through with your static equilibrium.